Right, I'm back. Right, guys. Okay, this is round 2, attempt number 2 since I had internet issues. Nikita should be joining me on the stream shortly. Okay, so this is the IAL Edexcel, so International A-Level Edexcel Chemistry, Unit 4, January 2020 paper review. Like I said previously, these papers, A2 papers are hard, no matter where you're coming from. You realize that it's all to do with the practice and making adjustments when you make mistakes. The questions are relatively repetitive. You get to see certain questions which appear every year, and those just need to be practiced. Also realize that some questions are going to be quick, some questions are going to be more slow. And so looking at kind of adjusting your time for each of those, but realizing that there's going to be differences in time. So if you find one that's taking longer than others, then that means it directs you in terms of where you'll need to be practicing. So that's okay too. I was saying in my previous one that crashed, students often ask me whether or not I would score 100% on a paper, and the answer is hell's no. These papers are hard. A2 chemistry is tough. This is like the end of this is after covering all of the topics, everything, and this is challenging this. So if I was going to be sitting an exam, I'd be doing all the papers I could just to get my practice in to make sure that I'm consistent. Hi, Nikita. So lovely to see you. Glad you could come along. So Nikita, you're going to be asking me lots of questions, I've no doubt. I'll do my best to answer them. Right, I'll put the chat up, so I'll just load up my YouTube. Oh, hang on, let me do that and go, right, open in YouTube. Put that on my other screen. So this is the January 2020 paper. Now, just so you know, the January set exams only had a Unit 4, didn't have a 5 or a 6. So I only have to do one of this series, which is quite nice. Right, I will pop out the chat window. Nikita, I've posted this paper onto your Google Classroom for you guys to all have a go at. Are you going to do it and follow it with me, or have you already had a go at this one? Right, let's share screen and crack on. Share screen. I'll also then change to my clip cam because I've no doubt I'll be doing some dancing around in this particular webinar, trying to explain certain questions. There we go, all up and running. It's looking good. Do it as I go. That's fair enough, Nikita. Sounds like that's just going to be great. That you can be in a bit of a competition. I like that. I just saw it. Fab. Okay, right. Let's crack on, guys. So I'll get rid of my keyboard from my laptop. Hopefully my pen's all charged. Ugh, get rid of my keyboard. Right. Okay. We're up and running. So January 2020. This is me versus Nikita. So this is Mr. Duncan's exam. It'll be interesting to see if you disagree with me any of the questions. I'd like to think that you would. It's going to be entertaining. Okay, section 1, multiple choice. This question is about organic compounds with 5 carbons but different functional groups. An acyl chloride, 1, 2, 3, 4, 5. So pentanoyl chloride, pentanal, pentantuone, and an amide. Pentanamide. That's nice. Which of these, when mixed with water, produces a solution with the lowest pH? Well, the acyl chloride are commonly known as acid chloride, so that's going to be like pH 1. An aldehyde won't really dissolve it will dissolve in water, but poorly. Neither will the ketone, especially at these length of chains. The amide definitely will dissolve, but it's not going to be particularly acidic. In fact, it'll be basic, so the answer is going to be compound A. Nice, easy start, I feel there, guys. Which of these reacts with ethyl amine to form an N-substituted amide? Okay, so they're continuing this theme. So reactions with an amine, it's going to be number 1 again. The acyl chloride is going to go through nucleophilic addition, elimination with the amine to form an N-substituted amide. The aldehydes won't. Well, in order to react aldehydes and ketones to go through nucleophilic addition. You're going to need a much stronger nucleophile, and amine's not going to give a good one there. And then the amide isn't going to react with an amine. They're both bases. They're going to repel each other. Which of these reacts with iodine and sodium hydroxide to produce a pale yellow precipitate? So this is the iodoform test. So we're looking for the iodoform test, which is what we're looking for here, is C double bondo CH3. That's the structure we know that reacts with iodoform. So in this case, it's gonna be the ketone. It's gonna be number 3. Usual kind of chemical tests in the multiple choice. I like it. Which of these molecules can rotate the plane of polarized light? Oh, which one's going to be optically active? Who's going to have a chiral center? Eek, that's not particularly nice, actually. I'm going to end up having to draw them all out. I'll start with the first carbon. So that's got an amine and an amine group. It's got a H, got a H. So that one's not optically active because that carbon there has 2 groups attached. That's the same, so not optically active. Let's go for B. Now, you'll notice that this is taking more time than the others. That's okay. The first 3 were quick. So this is also, by the way, not going to be optically active. None of these carbon atoms, because they all have the 2 hydrogens attached, neither of them are going to be optically active. The next one, this one's looking promising. I've got a carbon which is connected to a chlorine, which is connected to 2 hydrogens, so that's not optically active. Connected to a CH3 group and a Cl, and there's my optically active compound. There it is, the answer being C. Next, if you're wondering why D isn't, this carbon's connected to 2 methyl groups, which prevents it being optically active. A polymer is prepared by the reaction between hexane dioalkyl chloride and hexane 1,6-diamine. They're forming nylon 6,6. Nice. What type of polymerization occurs? It is a condensation polymerization. Addition would be a polyalkene of some variety. The compound, ooh, that's grim. It's got a C double bond in the middle, and then it's a dioic. Ooh, that's clever, isn't it? That's you're gonna have, so that's gonna be a very fun one to name that. So that's gonna be a bute. It's a 2-ene, but then the A-butina. Oh my goodness, that's weird. Butina dioic acid. I'll even put in the one. Yeah, because the A goes back for a dioic. Yeah, for diene. E goes back. Butene with the E dioic acid there. 1,4, by the way. Fascinating naming, dioic acid. By the way, I know that's extending my time. It's just a fun game to play, isn't it? Bute-2-ene, is it? Oh, and I have drawn the Z version, so I'm including that too. Nice that. Or what? Bute-2-ene 1,4-dioic acid. I like it. Nice. And as I said, I've drawn the Z. Which of these organic products forms in the reaction excess sodium hydroxide? I'm going to remove both of those and put on the NAs. It's going to be A. Yeah. By the way, the alkene group, if anyone's wondering why the alkene group doesn't do anything, sodium hydroxide is a nucleophile. And nucleophiles are lone pair donors. It's going to be repelled by a carbon-carbon double bond. That will not touch the double bond. It'll only have the Na swap out and act as a base. Nice stat. Yeah. Neat. Moving on. Okay, question number 5. Which diagram shows the mechanism of a second order reaction between a 1-bromoethane and potassium hydroxide? Oh, second order. So that's going to be an SN2. Yeah, because second order means that you need both reactants to have to be first order. So in this case, this is an SN1 reaction because it's going through a thermal decomposition to form my trigonal planar intermediate. Yeah, and then subbing on. So that's an SN1, so it's not him. Yeah, this one is also an SN1, but the arrow's garbage going in the wrong direction. So it ain't that guy. That's just rubbish. Then we've got this one. This is an SN2, so it is a second order overall, and all curly arrows appear to be correct. So I'm going to say diagram 3 because the diagram 4 has a garbage arrow. So diagram 3. Which of these reacts directly with ethanoic acid to form ethanoyl chloride? Oh, nice bit of transformations there. To turn an OIC into an acyl chloride, we're using PCl5. Which of these changes has the largest increase in entropy? Solid to liquid. By the way, here's the graph that you guys have to remember for this. So increase entropy increases with temperature. Then you get a little step up for a change in state from solid to liquid. And then a big step up from liquid to gas. So far, this A fits in there. B is liquid to gas. There's B. This is a liquid and a gas going to aqueous and aqueous. That's going to be a decrease in entropy, so that's not that guy. Graphite to diamond, tiny change in entropy. Tiny. It is actually a decrease, by the way, so the answer is B. Equal amounts of W and X are mixed and allowed to reach equilibrium. The value of the equilibrium constant is 4.85. Equilibrium the mixture will contain almost all. Okay, so the equilibrium constant is above 1, which means there are more products than reactants, but it's not enormous. Like, you can have KCs in the value of the hundreds and even the thousands. So almost all, no, because that would probably mean irreversible. This one would be almost W and X. That would be a very low KC. You're talking 10 to the minus 5, 6. Like, you're talking acid-base equilibriums there. W, X, and Y. So we definitely could have a mixture of all of them, but there is less Y. There is less Y and Z compared to W and X. No, that's not correct, because the equilibrium constant is above 1. We know that the equilibrium constant is linked to product. So in this case, it's above 1, meaning more product. So we've got more Y and Z. The answer is D. Next, entropy of solution in a stupid Born-Haber setting. Hate that. So I don't like that picture, by the way. Whenever I do this, I do it as a Hess cycle. I know this is actually an example of a Hess cycle. It's just a Hess cycle I don't particularly enjoy. So what does X represent in the diagram? I'm going from gaseous ions to aqueous ions. This is the sum of the hydration enthalpies. Sum of the enthalpy changes of the hydrations of the gaseous ions, A. Enthalpy change of formation is enthalpy change of formation is not there because formation is from its standard elements in their standard states to form the salt. So heat energy change when 1 mole of a compound is formed from its constituent elements in their standard states and under standard conditions. Enthalpy change of solution is solid to aqueous, which is there. There's delta H sol. And then lattice enthalpy is gaseous. Lattice enthalpy is, we always assume formation, so that there is lattice, there's lattice enthalpy, LE, lattice enthalpy. How are 20 centimeters cubed of 0.05 sulfuric acid and 20 centimeters of 0.1 ethanoic alike? Okay, they've done a clever thing. That's diprotic. So we've got the same moles here, same moles of H+. That's what we've got. Both of the same pH. No, that's incorrect because that one's a weak acid, partially ionized. Even though we've actually not got the same moles of H+. Forgive me. We have the same moles of acid, but the same pH, no, because not all of the acid dissociates in weak acids like ethanoic, so the same amount of H+ is incorrect. Same amount of acid, yes. Have the same total concentration of ions? No, that's not true, because the ethanoic acid, once again, not dissociating into ions. Have the same total concentration of negative ions? No, that's still incorrect. They're just repeating themselves. Require 20 centimeters cubed, 0.1 mole for complete reaction. That is correct, because even though the weak acid is in equilibrium, when you add the sodium hydroxide, you push the equilibrium in the direction of dissociation. So the amount of amount of sodium hydroxide required for neutralization is the same. Next, which two solutions, both of concentration 0.1, have been used to produce this curve? So we've got a weak acid, that is a weak acid and a strong base titration. So we've got a weak acid, which could be B or D. There's my weak acid. Strong base, potassium hydroxide, nice and easy. See, do you know what? We're up to multiple choice 12 here. And actually, it's nice to look at the ones that have taken a bit of time. Like, ones really that have taken me most of my time. That bloody chiral center one is a pain, but otherwise they've been relatively speedy so far. Maybe I'm talking too soon. Maybe. A solution of sodium hydroxide with a concentration of this has a pH. Okay, Kw equals H plus, OH minus. We've got the OH minus concentration and we know Kw, 1 times 10 to the minus 14, reorganize over 0.008 will give me the H plus concentration. Need my calculator for the first time. I'm just going to put on my little fan. My laptop's getting rather wham. Right, so you've got an OKW. 1 exponential minus 14 divided by 0.008 equals minus log answer. And I got 12. Oh, okay. That's interesting. Between 11 and 13. It's 12. Spot on. It's interesting, that. Weird. Next. Okay, a student carried out an experiment to determine the equilibrium constant for the reaction of ethyl ethanoate and ethanoic acid. Okay, so we've done a series of different amounts of each substance were added to the conical flask, each containing that much hydrochloric acid. That's our catalyst for the reaction. The flasks were stoppered and left for a week to reach equilibrium. Each mixture was then titrated with 1 molar sodium hydroxide. In which flask was the equilibrium approached from the right side of the equation? What a horrible word. Approached. It's very odd. I'm assuming what it means there is which one's lying to the right-hand side. I can't... Approached. Which one is approaching it? Which one's approaching the right-hand side? Which one's... I don't like the word. I have to make an assumption there, guys. So, okay, conical flask number 1, acid, hang on a minute. Acid, which is a catalyst, HCl, so we can basically ignore the acid. Water is here, so this is right-hand side, and ethyl ethanoate, right-hand side. So 1 is lying heavily to the right. We're approaching it from the right. Number 2, we've got HCl, which we ignore. And then we've got left-hand side and left-hand side, the OIC and the OL. Number 3, we've got OIC and the OL again, left-hand side. And the next one is right-hand side with only 1. So I'm going to say, R and R, I'm going to say 1 and 4. That's where they're approaching this from, 1 and 4 only. The other 2 are approaching from the left. Seems reasonable to me. Which of these statements explains why it is possible to titrate the reaction mixture directly to find the equilibrium constant? Well, you're going to have to do it briskly, but sure. So what they're talking about here, guys, is when you set up a conical flask, just a bit of explanation here. They're setting up an equilibrium. They're adding their 3 substances. Their HCl catalyst, in this case, they're approaching it from the left. Their OL and their OIC, we're approaching from the left here. Yeah, and then they stopper the flask. Now, what they're then saying is, in order to determine the equilibrium mixture, what they actually do is they're looking for the OIC. So what they then do is they titrate. They'd set up a conical flask with just the HCl. They could then titrate that to know the exact amount of HCl that they added. Then they can titrate the equilibrium mixture entirely to work out the amount of sodium hydroxide used. You minus away the acid catalyst. You minus the acid cat, and that will give you the Na used in reaction with the OIC that's left over. Therefore, you can subtract the leftover OIC from the original OIC that was put into the flask, ORI OIC, and you'll get equilibrium OIC. That commonly happens. I'm assuming this is where they're going with this. But the reason why they can titrate it directly, see, usually what you do is, the sodium hydroxide is going to shift the equilibrium. Now, they're saying that you can titrate this directly. Now, the question is, how could you titrate this indirectly? How could you titrate it indirectly? Well, I guess what they'd probably mean is that they'd add some kind of quencher. They'd probably neutralize the acid. Oh, yeah, that's what they'd do. The indirect one, they'd add a sodium carbonate to the mixture and then neutralize all the OIC and then titrate with the leftover base. That'll probably be more like indirect, but interesting question. The answer is because the equilibrium reaction is slow. It's not going to adjust very quickly to the addition of sodium hydroxide. Sodium hydroxide quickly hydrolyzes the ester. That's definitely not correct, because if it did, you couldn't directly titrate. All the reactants and concentrations remain constant during the titration. Well, I don't think that's really possible, is it? A buffer solution forms in the reaction. Ooh, sodium hydroxide. It does. Ooh. A or D? I'm going to stick with A. Oh, yeah, I'll stick with A. But the first real one of interest there. It does. But by the way, it does form a buffer solution. Reaction mixture directly to find the equilibrium concentrations. Well, the buffer solution, it's not. It's not going to matter. It's not going to matter. I don't know. Oh, I hate rate graphs. Reactant Q is converted into two products. Okay, so Q is being decomposed into R and S. Sure. Which of these graphs shows that this reaction is first order with respect to Q? Okay, we know in rates, the mark scheme says A. Oh, Nikita, you're such a sweetheart. Nikita's checking the mark scheme as I'm going. Oh, that's so funny. That's nice. I'm happy to know that. Don't tell me any more, Nikita, just because I find it more entertaining at the end to see if although, actually, I'm glad that you did that in some respects because it means I make the solidification of that knowledge. Like, it's nice to know you can directly titrate because the reaction is, the equilibrium is slow, so it won't adjust. It won't move too much when I titrate it. So in rate graphs, in rates, oh, I hate this stuff. So in rates, we have two graphs. We have the concentration of the reactants, the concentration of reactants over time. These are our half-life graphs. Now, in half-life graphs, you can get like this and then this. And that a straight line is zero in these graphs. That is order 1 and that is order 2 in half-lives. But then we also have the other one, which is rate over Q's concentration. And if I've increased the concentration of Q and the rate remains 0, that's 0. I've increased the concentration. So this graph here suggests suggests 0 order with respect to half-lives. So that is definitely not first order with respect to Q. It suggests 0. That one suggests 0 because if I increase Q and the rate doesn't change, then it's having no effect on the rate of reaction. So that one's not correct. There's my first order reaction. That's a weird one. Half-lives with nothing changed. Q's a catalyst. Isn't that clever? The graph is 3. Next. This question is about the kinetics of a reaction between nitrogen monoxide and oxygen. The rate equation for the reaction is this. Okay. Which statement is not correct? I hate these. Hate them. Not correct. The reaction is third order overall. Yes, that is true because the sum of the orders is 3. Second order with respect to NO. First order with respect to O. Total 3. The units of the rate of reactions are moles per dm³ per second. That's always the units of rate. I don't know what the problem is with that. That's correct. The rate of reaction increases when pressure increases. That's always true. Always true. When the concentration of nitrogen monoxide doubles and the concentration of oxygen quadruples, the rate increases by a factor of 8. Now, I know that that's going to be wrong because the other 3 are all definitely correct, but I'd like to do the maths on it. So what they've just said is the rate will increase by a factor of 8 when nitrogen monoxide is doubled times 2 squared and the oxygen is quadrupled, and that is to the power of 1. So what we can now say is that we can say the sum of the can do it in 2 steps. So 2 squared, calculator, 2 squared equals 4 times by 4 would increase by a factor of 8. Nitrogen monoxide doubles and the concentration of oxygen quadruples. The rate increases by a factor of 8. Ooh. Well, I know that's wrong. It's first order. That should be true too. Oh no, Nikita, say nothing. Oh, hang on a minute. Hang on. Hang on. This is clever, isn't it? Let's do a rate value. K remains constant. Let's just treat K as 1. Let's go for rate equals 10 equals K, which we will put as 1, so we can just ignore it. Let's now go multiplied by 2 squared. So 10 times 2 squared gives me 40. After the first step, that would give me 40. And then I'm doing times by 4. That's clever, that, isn't it? Times 4. So 40 times 4 equals 160. We haven't gone up by a factor of 8. We've gone up by a factor of 160. In that by 16. Oh, that's clever. No, don't tell me the answer. Because 2 squared times 4 is 16, not 8. Yeah. I just had to do it stepwise. I love that Nikita's contributing. Well done, Nikita. What are the units for the rate constant for this reaction? Ugh. Okay. So the rate constant. So rate equals moles per dm cubed per second. Reorganize the equation. There are NO is concentration is moles per dm cubed squared, and so that's another one. Moles. I do this a funny way. Sorry if everyone doesn't like this. This here are 2 units because NO is squared. Yeah, because it's to the power 2. And then I've got moles per dm cubed for oxygen. Yeah, because it's to the power 1. That cancels with that. These two now combine and you flip it. So this is moles to the power of 2 dm to the minus 6, but now it's s to the minus 1 over it. So bring that up and flip the signs. So moles to the minus 2. S to the minus 1. Why do I seem to have funny units of... Oh, they're mean. Ugh, they reorganized it. That sucks. Don't like that game. You mean at Excel. Oh, Nikita, did you see that? Oh, how evil. An experiment was carried out. Blimmin' heck, that was so mean. So mean, that. You have to flip the powers, guys, to bring them back up. So it becomes mole to the minus 2 dm to the plus 6 s to the minus 1. Super mean, that. I was like, where's it gone? I'm a stupid pig. An experiment was carried out with 1.1 times to the minus yada yada yada. The numerical value of the initial rate, and the rate constant is this. What is the initial concentration? Right. So they just want me to insert everything into the rate equation. So the rate equaled K NO to the power of 2 and O2. Right, insert my numbers. The initial rate, so that's 3.2 times 10 to the minus 3, equals rate constant, 1.7 times 10 to the 3, multiplied by concentration of NO to the power of 2, times by, and they've given us oxygen. So this is oxygen, which is 1.1 times 10 to the minus 2, to the power of 1. Right, reorganize. So just bring both of these two over to the other side. So that becomes over 1.7 times 10 to the 3 times 1.1, times 10 to the minus 2. They disappear from that side. And then don't forget to root your answer. So 3.2, I'm going to do the bottom number first. I'm going to do these two first. 1.7 exponential 3 multiplied by 1.1 exponential minus 2. Now that gives me 18.7. Okay, now I can do 3.2 exponential minus 3 divided by 18.7. Gives me that, which is, so I've done this divided by this, which gives me 1.71 times 10 to the minus 4, root answer, because that I've just worked out the squared value, root answer, and I get 0.0. Oh, that's interesting. My calculator's given me in non-standard form. Eng, 1.308 times 10 to the minus 3. Oh, sorry, 13.8. That's really stupid. Shift eng. Yeah, okay, that's fine. It's A. Yep, fine. Moving on. Oh, section A is finally done. Blimey. That was multiple choice still. Tough, man. Okay, moving on to section B. That's nice, by the way. So, guys, let's have a look at my time. 30 minutes dead on. 30 minutes to do. I've just taken 30 minutes to complete the multiple choice. That was quite tough, that. I've done a bit of explanation, but it's not great, that, is it? Because it's out of 20 marks. I'm 10 minutes over. I'm going to have to find 10 more minutes. Okay, so NMR, I like it. They've given us a graph, given us a molecule. The compound ethyl-3-oxobutanoate, nice, which is used as a food flavoring, has the formula. High resolution NMR, identify which groups of hydrogens are responsible for each peak. Okay, so first fact, guys, I will do a webinar, by the way, on NMR. I need to do it sooner rather than later because I know you're running out of time for revision. Maybe I'll have a go at it tomorrow. But NMR, it's all about split pairs. I've got a split pair here, a triplet and a quartet. Now, what those two there tell me is CH2CH3. That's what that says. I'm doing this in green. It gives us a section, a split pair. So I can find that there. Now, what that now means is now that I've got that, this triplet is being split. It was the original peak split by two people next door. That's this guy. So I'm going to circle him and put Z. Next one, I'm going to then say that this one, I'm going to circle him and put W. Fine, because that was the original peak, which is the taller one, and then three clones next door caused by the three next door hydrogens. Yeah? So that's Z and W. The next one, I've got two singlet peaks. So I've got Y, which is higher than X. So it's got a bigger integration, but still a singlet. So this one's going to be there. That's Y. And this one, therefore, must be X. Nice. I like it. The reason being is they're both singlet peaks, but this one has three hydrogens, so it will have a bigger integration. And this one only has two hydrogens, so it's going to have a smaller integration. Done. Moving on. Explain the splitting patterns at the peaks of 4.2 and 1.3, the triplet quartet. Okay, so peak at 4.2 ppm. 4.2 split into a quartet is a quartet. That's probably going to be 1 mark, by the way. Is a quartet due to 3 non-equivalent due to 3 non-equivalent hydrogen atoms on adjacent carbons. Next, peak 1.3 was a triplet. ppm, peak 1.3 ppm is a triplet. What I'm assuming is the mark scheme is going to probably say that there's 1 mark for triplet quartet for those two names being correct. And then a correct statement about the non-equivalent hydrogens is a triplet due to 2 non-equivalent hydrogens on adjacent carbon. That'll do. Next, carbon-13 NMR spectrum, it has 6 peaks. Okay? Draw the structure of an isomer of ethyl-3-oxobutanoate that contains a carboxylic acid group, a ketone functional group, but only has 4 peaks in its carbon-13. Right, that's a bit mean, that, to be fair. 6 carbons. So, okay, this is a puzzle. I need a carboxylic acid. They've told us the sections here. Let's draw them out. I need a carboxylic acid. I feel like I want to give myself a bit more space here. I've got a carboxylic acid group. I've got a ketone functional group. So in C13 NMR, to reduce peaks, you need to add in symmetry or branching. To reduce peaks, add branches. Yeah? So what that means is I need to work out the total numbers. So that has 1, 2, 3, 4, 5, 6 carbons it needs to be a ketone. Does it say 1 ketone or 2? So 6 carbons. 6 carbons, how many hydrogens do I have? It's not, does it give me the molecular formula? It hasn't, I've got to work it out. 6 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. This is the puzzle, by the way. And oxygens, blimey, how many oxygens do I have? 3. Oh, okay. So that makes it a little bit easier because all the oxygens have been used in my groups. So, okay, add branches. 4 peaks in its NMR. It's tricky, that. Interesting. Well, okay, draw stuff. Guys, we've got to get on and draw stuff here. We need branches, so add some branches. Because if I do, about 3 branches would be great. 6, yeah, because that would be 1. Can I do that? Does that work? It is a ketone. It is an OIC. I think that works. Let me show you where that now comes from. So, guys, I'm really sorry. Trying to teach this as a concept is very challenging for an A-level teacher. I've just drawn a random molecule, and I think I've landed on the one I need. The reason being is what I essentially did was I just drew as many branches as I could and realized if I have 2 branches, that becomes a singular peak. And then I realized that if that's a singular peak, then I'm going to have everybody else. That will be 2, 3, 4, and 5. So I was like, oh, I'm over on my number of peaks. I need 4 peaks. So add another branch. Yeah, if I now have 3 branches on the same carbon, that now becomes a single unit, and these are a single peak. So I get 1, 2, 3, 4. It's really hard, that. It's difficult to explain, and you can spend hours on that one. And it's 1 mark. It's meant to be done in 1 minute. It's the correct answer. Does it ask you to say to draw the structure? There's my answer. I'm going to move on at that point, guys. If you want to know how to name that, it would be 3,3,3 dimethyl 2-oxobutanoic acid, swapping the ketone into this prefix. Beyond A-level, that. Okay, a chemist synthesizing ethyl 3-oxobutanoate looked for the presence of looked for its present in the reaction mixture using thin layer chromatography. The solvent used was a mixture of ethoxyethane, which is polar, and hexane, which is non-polar. It's interesting that they told me that that guy's polar and they haven't mentioned it to the other guy. Under these conditions, the RF value for ethyl was 0.45. Complete the diagram below showing a chromatogram for ethyl, including appropriate labels. Okay, first thing, baseline. Baseline done in pencil. We're then going to put on our dot. Now that dot's going to run. So we now need to do solvent front. By the way, you'd have to use a ruler for both these, I believe. So I'll do that. Now, here's the clever part of this question. I shouldn't really do it overhanging the edges. Shouldn't really do that. Shouldn't do the baseline either like that, really. Now, here's the clever bit. This is now the solvent front. It's a really nice question, this. Solvent front. So we now need to create an RF value of 0.45. It's really clever. Now, what we know is that RF value is the dot over the solvent front over the solvent. Now, if that value there is 0.45, I can now measure the line I've drawn from the baseline. This will be the solvent front. So I'm going to put that right there. So I'm going to go 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters, 6 centimeters, 6.8. So my solvent is 6.8 centimeters. Shouldn't actually be in centimeters. Should actually be in millimeters. 68 millimeters, even though actually I don't think they really care in Excel's case. So now what we can do is we can reorganize this and do multiply by 68 millimeters. And that'll give me where the dot should be. It's a really clever question, really like it. Times by 0.45 gives me 30.6 on the dot. So I now need to go 1, 2, 3, 6. There's my spot right there. Remove all those. There we go. I'm done. That's it. Oh, but it'll need to be above the guy. There we go. I probably don't want to do it as a line like that. I'm probably going to do it as a dot. Yeah, it doesn't really matter as long as it's spherical and I measure from the middle. That'll do. I shouldn't make the dot bigger than the... Oh, okay. You get the point here, guys. You get the point. That'll do. I'll take it. Might be too big, but... Suggest why the RF value is significantly lower than 0.45 when just hexane is used as a solvent. Okay, so this is to do with affinity for the mobile phase. We know that the RF value, if they ask you to explain why that dot is there, you would say that it is due to the affinity at the spot. The affinity for the stationary phase is equal to the affinity for the mobile phase. So therefore, the dot stops moving. You could also slash. It is dictated by solubility in the solvent from GCSE. Now, in this case, it is AL, so I'm going to assume that they're going to want me to talk about affinity. And if they've changed it for a non-polar solvent, which is just hexane. So I'm first of all going to say that the hexane is a non-polar solvent. Non-polar solvent. So ethyl 3-oxobutanoate will have a lower affinity for this mobile phase due to only being London dispersion forces. London dispersion forces. What I'm doing there, guys, is I'm probably going way OTT here because it's 2 marks. I'm assuming 1 mark for saying it's non-polar and the next mark for saying it has a lower affinity for it, so it drops out earlier. Assuming that's what I'm asking. So it'll be very interesting to mark that. Don't tell me, Nikita. Only London dispersion forces. So won't travel as far. So will reach a lower height. So will reach a lower height. Next. It's going to be interesting. That one I love. Really love that one. I'm excited to mark it. That's nice. Compare and... Oh, God, this is epic. How many marks is this? What? 6. Yeah, I'm assuming this is bringing me to the end. Oh, no, it's not. I'm still on section B here. Holy moly. Compare and contrast the reactions of propanal. Blimey. I feel like I am not going fast enough on this paper. I definitely need to increase my pace here, but I'm not really too fussed. Compare and contrast propanone. I'm drawing them out because if I don't draw them, I just can't see it. Okay. 1 oxidizing agent. Okay. Compare and contrast reactions of propanol with 1 oxidizing agent, 1 reducing agent, and 2,4-DMP. Okay. So, choose an oxidizing agent. Acidified potassium dichromate. Seems very reasonable. Yeah. And both of them would react. Would they? No, they wouldn't. No, they wouldn't. The ketone's not going to oxidize. It's going to resist oxidation, isn't it? So using potassium dichromate, acidified potassium dichromate, using acidified potassium dichromate, oxidizing agent, propanal. Do you know what? This is a 6-mark question. I wish I had my stopwatch on so I could time this. Actually, agent propanal will be oxidized to propanoic acid. Propanoic acid. In your answer, include relevant observations and reactions you discuss and equations for any reactions classified as oxidation. CH3, CH2, CHO plus oxidizing agent becomes CH3, CH2, COOH. Does that balance? It does, amazingly. That's nice. So there's the oxidizing and the observation. That's what I'm going to switch over to here. Observation would be orange to green. Orange to green. Propanone won't react. Propanone will resist oxidation. Will resist oxidation. Next, reducing agent. Reducing agent is LiAlH4, lithium tetrahydroaluminate. Now, you do not need to be able to name that. By the way, Edexcel IAL demands LiAlH4, which is really nice. Cambridge demands you to know both the sodium tetrahydroborate plus lithium tetrahydroaluminate, and realize that the LiAlH4 is stronger, where AQA demands you to know sodium tetrahydroborate only. It's really weird. But anyway, reducing agent is easy for Edexcel because it's just that one. The other one, of course, is tin and HCl for nitrobenzene phenylamine, and of course, nickel and hydrogen gas, 60 degrees. That'll do anything. It's non-selective. Reducing agent, both will work. So I'll just turn them back into their alcohols. Reducing agent, both will react. Both will react. Propanal will form propan-1-ol. Propan-1-ol, but propanone, you don't have to write an equation for this one because it's a reduction, not an oxidation. But propanone will become propan-2-ol. Next, what else do I have to do? 2,4-DMPH. They're both going to form a yellow precipitate because of C double bond O. And we could then recrystallize them and check their melting points and identify exactly which one was which. With 2,4-DMPH, 2,4-DNPH, both will react. Both will react to form, let's see, oxidation is. To form a orange precipitate. Orange PPT. I think I'm done there, guys. I don't want to do any more. I'm done with that. Whatever, moving on. I haven't even used the second page. Lol. Right, on to kinetics, on to rates. Oh, I hate rates. Okay, the rate constant for the reaction to convert cyclopropane to propene was determined at 5 different temperatures. Okay, so complete the table, I'm assuming. Complete the table. So this is lnk. There's k. So just ln it on your calculator. ln 1.66 exponential minus 3. What's my number? Minus 6.40. What's nice about this, guys, is it matches the theme. So I know I'm in the right kind of ballpark figure. Do remember that's been deliberately done to 6.40. People, you can't forget that second decimal place. They'll penalize you. Watch out. The next one is, this is 1 over temperature, and there's the temperature. So I just need to do 1 over 840. Should be again in the right ballpark figure. 1.19 times 10 to the minus 3, which fits the trend. Oh, no. I don't want to plot a graph. They take so much time. Okay, plot a graph of lnk against 1 over t. So, right, now just to explain to you how I do this, I do Steve against Sarah. So, Steve against, so the 1 over t is on the x-axis. This is 1 over t, and that's going to be k. They really get me. Okay, so they've given us some graph paper. That was close. I nearly drew the whole thing out there. That would have been a full-on nightmare. That would have been a waste of time. Okay, so I've got 1 over t and k. Okay. How would I probably do this in an exam? I would probably just use the entire grid. I'd probably use the entire grid for my lines. Then I'm going to look at my numbers and go, how many squares have I got here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Right, look at my values. So 1 over t is on the bottom. So 1 over t is on the bottom. And the units of that are Kelvin to the -1. Steve against Sarah. ln k against 1 over t. Yeah, that's okay. So, and this is now going to be ln k. Right, so the 1 over t, 1 over t is going to be, well, let's do the ln k, it's easier. So the ln k, look for the largest number. Here's the largest and here's the smallest because it's going negative. So this is an interesting graph, this. So if that's the largest, if I go larger, let's go to -1. So this would be -1, and I'm going to go to the smallest at -11, which is a gap of 10. So 5. So -1 going to -10. So that's going to be -3, -5, -7, -9, -11. What that means, that'll put me right from here. So my actual numbers I'm using are from here to here. Is that right? 10.6, a bit higher. That's pretty good. I'm quite happy with that. Now, I need to be very aware here that there's no units. So that's okay. I'm happy to take that. Next, 1 over t. This is another nightmare. So my largest to smallest, my smallest is him. My largest is him. They're all 10 to the -3, so I can put that in the units on the axis. So I'm going from 1.1, so I'm going to go from 1.1 to, no, I'll just go from, 1.1 to 1.4. That seems reasonable. So now how many numbers is that? So that's difference of 3, so 6 would be useful. So if I go to 1.1 and then 1.2 and then 1.3 and then 1.4, how does that put me in terms of my numbers? It's not bad. I'll take it. It's the best I can do, I think, here, guys. Now, I need to make sure that I put down here times 10 to the -3 in my little bracket, just so I can do. You can add it to each one number if you want, but that's just the way that I would do it in my exam. Okay, now I get to, so by the way, this is taking an exorbitant amount of time. I hate these graphs. They take so much time. So now I've got to plot each value. So, okay, just take it one at a time. So ln k minus 1.8 to 1.12. ln k minus 1.8. I've made a mistake already. I hate graphs. These do need practice, guys, genuinely. The reason being is I'm going more negative as I move up. It's meant to be the other way round. And I always know that they do this. So I need to flip this. I need to flip it. 9, 7. It's upside down. 5, 3. Gone upside down already. 1. What a nightmare. Because now I'm coming down my axis as we always are. Could I have put the axis at the top? The x-axis at the top? I could have. No, but then it still would have done the same thing. It's the equivalent to me having the line at the top. Yeah, anyway. No, I don't like it. Anyway, we'll watch later after I do the paper. No problem. So this is taking me so long to do. I'm running out of time. This is going to be shocking. I'm not going to finish the paper on time. Minus 1.8 and 1.12. minus 1.8. Well, if that's minus 2, 1.8 is here, but then 1.12 was it times 10 to the minus 3? Yeah, 1.12. This is 1.1, 1.12. That's a 10, so that's 1.11, that's 1.12. 1.14, 1.16, 1.12, 1.14, 1.16, 1.2. Okay, I've made a mistake there. That's 1.12, and that's 1.14. Yes. So 1.12 is there. So now I'm going to have to plot that. It's a horrible graph. I hate these graphs. There we go. Next. Okay. Next one, please. That one's done. Then at minus 4, 1.19. Minus 4, which is nice and easy. 1.19. Drop back 2. Minus 4. There. Next. Tick him off. Yeah. Take him off to the next, minus 6.4, minus 6.4, and 1.26. 1.21, 1.22, 1.23, 1.24, 1.25, 1.26. 1.26 on that line there. That's 6 minus 6.4. Yep, correct, done. Next one, 1.34 and minus 9. Well, thank goodness it's easy. 1. What? 34. 1.3. 1, 2. Nope. Nope. Yeah, 1.2. 3, 4. Yeah. Blimey, 9. Well, at least I'm seeing a dead straight graph, guys. That's all I can say. Mr. Duncan, your screen is so blurry. Oh, is it blurry? Have I lost my connection? Nikita, sorry about that. It's because I'm so far away. I hope that makes it a bit clearer. Last one, minus 10.6 and 1.39. Minus 10.6. 10.6, 246. 10.6 and 1.39, which is there. Should give me a perfectly straight graph. Nikita, is the screen any better? Blimey, that was hard. How is it now, Nikita? My internet connection doesn't say it's poor. How are we doing for time? 1 hour so far. No, it's not better. Oh dear, that's not great, is it? Because there's no point in me doing this if it's blurry. Nikita, maybe it's your connection. Broadcast quality. I'm sure I could increase that. Need to try that next time. I don't know what same. Oh, it was me. Do you know what though, Nikita? It's fine. It's okay. As long as it's okay, I don't mind. This question's taken me a ridiculous amount of time anyway. That was hard, that, guys. Really tough. Okay, use your graph to determine the activation energy. Yeah, this is super common, guys. So just to tell you, they've given you, it says, work out the activation energy. You should include the value in units of the gradient of the line. So this is y equals mx plus c. That's what this is. And you realize that m is the gradient. So the gradient is minus EA over R, which makes total sense because the gradient is negative. Yeah? So what I now need to do is work out the gradient. So the way I'm going to work out the gradient is take the longest points. And what this is actually pretty nice, to be fair, because look, where I hit the line there and there are nice equal numbers. So I've got to remember to take the correct differences. So we know that the gradient of any line, gradient equals delta y over delta x. Boys on top of girls, as I like to teach, because the Y chromosome over the X chromosome. So we've got the change in Y. Now our change in Y goes from -1 to -11, because we're actually on that, which is great. Yeah, so this is -1 to -11. So that would be, it's a difference of 10. Technically -10. Yeah. Over, and this is going from 1.1 to 1.4. This is quite nice. Over, and now remember, don't forget your 10 to the -3. Over, no, I mean, it's actually like 1.4 minus 1.1. Yeah, 0.3 times 10 to the -3. Okay. So that's my delta x, my delta y. Give me my g. It's going to be negative, a negative gradient since the line is going down. -10 divided by 0.3 exponential -3. Go. And I get a gradient of -3,3,3,3,3. Done. And my units, so my units for this are going to be, so activation energy is joules per Kelvin per mole, and R, the ideal gas constant, is, no, sorry, just activation energy is joules per mole. Joules per mole or kilojoules per mole, either one. R is joules per Kelvin per mole. So that's my gradient. Here are my units. The joules cancels and the moles cancels. We've got 1 over K to the -1. Bring it up, flip the sign. The units are Kelvin. Yuck. I hate all these games, guys. I hate it. Should include the units, yada, yada, yada. I'm done walking on. The activation energy for many reactions around, oh, hang on. Sorry, determine the activation energy. I wouldn't have spotted that if it wasn't for giving the information comment on your value. I would have just totally missed that. I've got 2 marks so far, I just haven't got the third. So what I now need to do is to say that G equals the activation energy over R, and it's negative. Well, my G value is -3,3,3,3,3 equals minus EA over R. Let's bring the R over, times R will give me negative EA. And then I can just invert it. So R, of course, is 8.31. Got to know that by now, folks. 8.31 multiplied by minus 3. Go. And I get a value of minus. Now, you can't have a negative activation energy. You can have a negative gradient, but you can't have a negative activation energy. And because my G was negative and the equation is negative, it flips it. Yeah. So that becomes an activation energy of, once I run all that through, I get 276,997 joules, not kilojoules, it's in joules. That's the activation energy. Or, if we like, 277 kilojoules. Now, it'd be interesting to know if it's in, kilojoules per mole for the activation energy. That's fair enough. Next, the activation energy for the for many reactions is around 50. Given this information, comment on your value. Our value is big. That is a big activation energy. Our value, activation EA in question A3. In A3 is very large. Is very large in comparison. In comparison to many reactions. Many reactions. I don't know why I switched to red. I really wish I hadn't. I can change that. There we go. That's definitely not what I want, though, is it? How bizarre. In many reactions. 2 marks. Well, the activation energy is very high. It means that it won't want to react. It's going to require high temperatures. High temperatures will be needed for reaction to take place. In comparison to other ones. Grim. Explain the trend in the value of the rate constant as temperature increases. Oh, that's nice. So we know as temperature increases, the rate constant K increases like that. It's an exponential growth. So first bullet point, K increases exponentially as temperature increases. Increases exponentially as temp increases. 1 mark. 2 more marks. Explain the trend. Well, in the rate equation, rate equals K multiplied by X to its power and Y to its power. Yeah? Well, the rate constant is that it's taking into account all the other factors, things like surface area and temperature, which don't change concentration. Now, in terms of temperature-wise, the reason why K increases and why it increases exponentially is to do with Maxwell-Boltzmann. So Maxwell-Boltzmann distributions like this. So they say to you, why does the rate of a reaction increase exponentially as the temperature increases? The reason being is if this is EA, yeah, all of these particles are the one with the temperature, the energy to react. Well, if you increase temperature, you shift the graph over, and all of a sudden you end up with loads more particles with the activation energy. So the explanation for that, due to particles gaining more kinetic energy, and so many more particles have EA, activation energy. I'd write in my real exam. I have no idea if I'll score 3 there, guys. Haven't got a clue. Still going on this paper. This question is about halide. Silicon tetrachloride is used in the manufacture of optical fibers. It can be made by the reaction of silicon carbide. Silicon carbide with hydrogen chloride using nickel catalyst. Okay, so we've gone into entropy. Okay, so at this point, guys, we're going to write down all my equations for this now. So number 1, delta S system equals sum of delta S super products minus sum of delta S reactants. I'm then also going to follow this up with delta S surroundings is equal to minus delta H over T. I'm then going to finish this off with delta S total. I'll write this underneath because I'm running out of space. Delta S total is equal to delta S system plus delta S surroundings. Just add them together. And then, yeah, and then we've also got delta S total is equal to R ln K. This is, can I just point out, guys, what I've just shown you is exactly how I teach entropy. Like, you just have to know all of these equations, and you just have to spit them out on recall. I'm going to walk us through every single one of these, and they're super handy just to be able to spit out. So just learn to spit them out. And it takes 1 minute. Give it the time. Right, first of all, calculate the total entropy change for the reaction using the information given. So I'm going to have to work all the way through this. It's 5 marks. Include a sign and units in your answer, given the appropriate numbers. Right, so the first thing I'm going to run is this one. I'm going to run system first. So I'm going to have to do, so run system first. I'm going to go back to my normal pen, and I'm going to go delta S system equals, right, sum of the products, products minus reactants. We need to do this first. So 1 methane, so plus 186.2, and there's only one of them in the equation, which is nice, brackets, plus silicon chloride liquid, yeah, which is that one, plus brackets plus 239.7. I'm going to put that in another double bracket and say minus brackets the reactants. So this is now 1 silicon carbide plus 16.5 close brackets plus open brackets 4 HCl's. 4 times 186.8. Now in my previous paper, I actually forgot to include that point value. I don't quite know why. Right, let's run that through our calculator. Now, in reality, in the exam, I'd want to do these in separate pieces. I'd do this as a piece first and then this, because I always worry that I'm going to make an error. But I can try and do the crazy calculator thing. Minus brackets, brackets, plus 186.2 plus brackets, oh, I see, I've missed a bracket now. Close brackets, plus 239.7, close brackets, minus open brackets, plus 16.5, close brackets, plus open brackets, 4 times plus 186.8, close brackets, equals. Right, so my delta S system is equal to minus 337.8, and my units are in the table, joules per Kelvin per mole. So there's my system. Now I do kind of want to check that again. Really tempted. Does that make sense? So this is like 400 odd. This is like, yeah, it seems reasonable because that's about 400. Yeah, okay, I'd say that was about right. So this is a big decrease in entropy. Would I agree with that? Solid, 4 gases going to a liquid and 1 gas. Yeah, it's a drop. I'd agree with that. Okay, reasonable numbers. Next one. Delta S surroundings equals minus delta H. There's my delta H. So this is minus brackets minus, that's the key thing, 631.3, yeah, over the temperature. Temperature is 298. Was right, wasn't it? Yeah, 298 in the question. Over 298. So I'm going to get the entropy of the surroundings. So minus brackets minus 631.3, close brackets, divided by 298. Gives me a value of plus 2. It's a bit rubbish, isn't it? Plus 2.12. 2.12. And that's going to be, that's kilojoules per mole per Kelvin. Weird, isn't it? Because the Kelvin comes up becoming -1 and the surroundings one is taking into account. I've got to be really careful here, guys. Got to be really careful. Because one's in joules and one's in kilojoules. It would be better for me to convert it all to joules, really. I can do that times 1,000. I prefer it. Turn it into joules, which is, I've just done on my calculator, 211. It's actually a better number anyway. 201 joules per mole per Kelvin. Right. Now I can finally get to delta S total, which is going to be equal to minus 337.8 in a bracket, plus brackets plus 2118. They're both in joules, so I can simply add them together. So that's going to be minus 337.8 plus minus 337.8 plus brackets plus 2118. And I get an entropy total of plus 1780. And that will be joules per mole per Kelvin, because they were all had the moles per Kelvin, so that's fine. Wow, long that. 5 marks, but definitely wasn't 5 minutes. Need to work on that faster. In the industry, the reaction is carried out at 700 degrees Celsius. By considering entropy and other relevant factors, justify your answer. Okay, so let's do entropy first. So the first thing to say is that the temperature 700 is higher than the temperature we used. Yeah, 700 is higher than what we did. So the first thing is at 700, the enthalpy, the entropy change of surroundings will be smaller, because what we'd be doing will be smaller. This is because we'd be inserting a larger number there, dividing that minus number. We can actually show you that. So that was the value. This was the value that was at 298. But if I did minus brackets minus 3631.3 divided by 700, then my value becomes 0.9 times 1,000, becomes 900. So it drops significantly. Basically halves of that temperature will be smaller. Now, what that then means is, well, if that becomes 900, imagine subbing in 900 here, it means that the entropy total is going to drop massively as well. The entropy of the system doesn't change so much. It would change, but not significantly. But my entropy total would also drop significantly by over 1,000. That would be smaller. So entropy change total would also be smaller. What that tells me is therefore a lower yield will be obtained. A lower yield will be obtained. It's less feasible. Therefore, less feasible. I like that, less feasible. Right, now I need to consider the other point, which is temperature and rate at a higher temperature, at a higher temp, rate will increase. I'm done. So I considered do you see how useful these equations are? Because you can basically understand exactly what they're doing there. You can see that the temperature occurring in system and then system adds into total. These equations are so handy, they're great. I haven't had to do anything, by the way. Oh, yeah, I have. Use your answer to calculate the equilibrium constant. Shrink. Delta S total equals RLNK. And that is the equilibrium constant. Right. So let's input my numbers. My delta S total was plus... laptop's having a bit of a break there. Plus 1780 equals R, which is 8.31, multiplied by LNK, reorganize, over 8.31 will give me LNK. LNK equals plus 1780 divided by 8.31, and I get 214.2. That's LNK. Now to get out of LNK, I need to E both sides. E the opposite. So E LNK gets rid of that. So I need to E the other side, E 214.2. And that's the opposite of the LN button. So shift LN 214.2, which is massive. K equals 1.06 times 10 to the 93. The equilibrium constant is massive. So at least we know that this reaction's unidirectional. Is it going to ask it? No, they can follow this up with comment on what this value for equilibrium constant tells us. We know that the equilibrium constant Kc is a numerical representation of the position of equilibrium, and that this is so massive it's going to lie heavily to the right. Nice. Right, on to Born-Haber's. Oh, man, this is tough. So, letter A, enthalpy change of atomization. Oh, yada, 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 yada. Right. So, complete the Born-Haber by adding in the letters in the box for the energy changes. Relevant species, arrows show directions up and down. Okay, so all the arrows going up here will be up. and up. This one will be down. And then the next one is dependent on what they give us, which is a negative value. There's the lattice energy, so that's coming down. Remember, a negative sign tells us an arrow comes down. A positive sign is when an arrow goes up. It's an energy profile. So, okay, I've got to put on the relevant people now onto these things. So I've got here calcium iodide. To make that from its ions from this shelf, I need 1 calcium 2 plus gas plus 2 iodide ions gases. Yeah, and that then, the next one is the so I need the calcium gas needs to become a 1 plus gas. I'm assuming first ionization energy. So that's going to become a calcium 1 plus gas plus 1 electron plus 2 iodine atoms. Right, and that value there is ionization number 1, which is B. The next one is, oh, no, that's B there. Yeah, ionization number 1. Ionization number 2 is here. That now becomes calcium 2 plus gas plus 2 electrons plus 2 iodine atoms. Now we're going to have electron affinity, the electron affinity for iodine, but times 2. So this is E times 2. Because there are 2 iodines and 2 iodides, and this value here is the electron affinity for 1. Yeah, and the last one is the lattice enthalpy, which is just F. Done. That was relatively easy for 3 marks, that, if you're well practiced. If you're not, that'll stuff you. Make sure you're practicing your Born-Habers. They're great questions for speed. Use the data to calculate the value for the enthalpy change of the formation of calcium iodide. That's right, so they want us now to work out this one. So start in the same place, end in the same place, all the way around. Right, so I'm going to zoom out so I can see both pages. So we're going to have, the equation's going to be question mark equals A is brackets. Oh, it's with me. First arrow. This one is with me. I'm going up in this direction and then down to that point. Start here. Yeah, this is the one we're looking for. Start and end of this arrow here. Yeah, the start and end. Come on, laptop, just behave, will you? This is what we're trying to calculate. It starts here and ends here. So we need to start at the same place, but go in the opposite direction. Up there and down there. Got somebody messaging me. I don't know why. I always worry. I know it's nice to check on this just in case somebody messages me telling it's all broken. So, okay, so we need A, and this arrow is now going with me. My journey is in this direction, and this arrow is with me, so it's positive in what am creating. So plus, it's with me. Now I need A's value, and A's value is plus 178.2, plus 178.2. Notice that plus there is still there. The reason by that, because it's telling us it's endothermic. This one is whether or not it's going with me or against me. So the next arrow, which is D times 2, is also with me, plus, what's D's value? So D's value is plus 106.8, plus 106.8, close brackets. Next arrow, it's with me. Oh, but D is 106, I need to times that by 2. So the next one, B is also with me, plus B is 1B, because this is the first ionization energy, plus 590, close brackets. The C is still with me as well, plus C. What's C's value? Plus 1145, plus 1145, close brackets. Next one, E is also going with me because my journey is down now. E is also with me. Yeah, so that's going to be plus brackets, E's value times 2. Now, E's value times 2 is minus 295.4. 2 times minus 295.4. I need to check that I've written down that number correctly. 295.4, yeah. And the next one, this one is also with me. Everybody was with me. Plus brackets F, which is minus 2074. Right, run all of that through. That's been a real pain that on for me because I don't have 2 pages next to each other, so I can't just move between the 2. Now I'm going to type that in on my calculator. So with me, brackets plus 178.2. Close brackets. plus, with me, brackets, plus 106.8 times 2, close brackets, with me, brackets, plus 590, close brackets, with me, brackets, 11 plus 1145, close brackets, with me, brackets, plus, nope, 2 times minus 295.4, close brackets, with me, brackets, minus 2074. Now, before I press enter, it's asked me for an enthalpy of formation, minus 538. That sounds very reasonable to me. Kilojoules per mole. It's exothermic, seems reasonable. Metal plus iodine, yeah, that's going to be exothermic. The value for the lateral enthalpy of calcium iodide determined experimentally by using the Born-Haber cycles differs significantly from the theoretical value. Explain why the Born-Haber and the theoretical values of the lattice enthalpies are similar for calcium fluoride but different for calcium iodide. Okay, so calcium fluoride, number one, is almost 100% ionic. However, calcium iodide has significant covalent character. Significant covalent character. Covalent character due to calcium 2 plus ion, calcium 2 plus having a high charge density, and is therefore polarizing, very polarizing. Iodide ions are very large and easily polarized. Done. That's all I want to do. The electron affinity for iodine, so iodine gas gaining 1 electron goes to iodide gas. That is exothermic. That is a negative delta H because I'm forming a bond between the nucleus and the electron. Yeah, it then said, explain how the electron affinity of chlorine differs. So chlorine gas plus an electron goes to a chloride ion gas. And that is also going to be exothermic. But the question is it going to be more or less? And in this case, we've got an iodine atom with 1,000,000 shells trying to gain an electron into that shell. Or you've got chlorine with 1, 2, 3. It's definitely going to be easier to gain the attraction. So the chlorine electron affinity, the electron affinity of chlorine is more exothermic. 1 mark is more exothermic. This is because chlorine atoms, Cl atoms, are smaller and form a stronger electrostatic attraction, smaller, less shielding. It's always nice to say smaller and shielding together. Less shielding. And form a stronger electrostatic attraction between the nucleus and electron. Done. Section B finished. Holy moly. God, how are we doing for time here, guys? Wow, 1 hour 30. Still going strong. Okay. So a bit of organics. This question is about ethanoic acid and some of its compounds. Student ABC carried out an investigation to determine the amount of isoamyl acetate, an ester of ethanoic acid in banana flavoring. The hydrolyzed ester with sodium hydroxide, the amount of sodium hydroxide was determined by titrating the reaction mixture with HCl. Give the systematic name for isoamyl acetate. Let's draw it out. If I was in the exam, no, you know what, it's reasonable that I shouldn't do that. In the exam, I would probably draw it here. 1 carbon, 2, 3, 4. Oh, they've even done the wrong formula. That's naughty of them. There we go. Always add your sticks. Right. So this is 3-methyl, because you'd always count from the O. 1, 2, 3. 3-methyl. This is 3-methyl butyl ethanoate. Yuck. Ethanoate. Tricky. Right. 6.06 times 10 moles of sodium hydroxide reacted with the ester present in 1.06 grams of flavoring. Calculate the percentage by mass of the ester in the flavoring. Okay, so we need to work out. So number one, the ratio between the sodium hydroxide and the ester was 1 to 1. So first thing that I can say is ratio 1 to 1. So 6.06 times 10 to the minus 3 moles of ester. Next, number of moles is grams over rams. Well, I've got the moles, and I can work out the rams. So now I need to work out the relative molecular mass of that guy. So that's going to be, it's horrible. It's going to be 12, first carbon, plus 3, plus 12, plus 16, plus 16, plus 12, plus 2, plus 12, plus 2, plus 12, plus, lost count, 1, plus 12, plus 12, plus 6. I think it might be 130, but I'm going to try that again. I'm going to give that another go. So I'm going to do it stage by stage as well. 12 plus 3 plus 12 plus 16 plus 16 plus 12 plus 2 plus 12 plus 2 plus 12 plus 1 plus 12 times 2 plus 12 plus 12 plus 6. 130 again. Okay, so I'm happy with 130. Reorganize. 130.0, by the way, it must be 0.0. Got to remember that, guys. 0.0 multiplied by 6.06 times 10 to the minus 3 multiplied by 6.06 exponential minus 3 equals 0.788 grams. Right, so I've got that many. So the percentage in the flavoring is 0.78. I'm actually going to use the real number there, 7878 over 1.07 times 100 equals answer divided by 1.07 times 100. There is 73.6%. I'm done. Moving on. The student used 25 centimeters of sodium hydroxide solution with a concentration of this for the hydrolysis. Calculate the pH of the reaction mixture when the hydrolysis is complete. Assume the total volume is 25. And they've given us Kw. So there's excess sodium hydroxide is what they're saying. So, so at that point, now because it's excess sodium hydroxide, it is not a buffer. It's just a simple excess calc. So the question is, what was our moles? What was the original sodium hydroxide? Well, they added that much sodium hydroxide. So the original, I don't know if it's the original or not. I'm just going to write down what they told us we did before. 0.06 times 10 to the minus 3 times 10 to the minus 3 sodium hydroxide was there. But they've now added, so new one that I've been given. I don't know, I shouldn't really call it original and new. I'm just working out the two numbers for sodium hydroxide. Because it's got to be an excess, otherwise it'd be a buffer, and this wouldn't be 3 marks, it'd be a mess. So I've now got C times V over 1,000, number of moles equals C times V over 1,000, and they've given us V and they've given us C, so let's just run them through. Number of moles equals concentration 98 multiplied by volume 25 all over 1,000. That'll give me the moles of that. So 0.98 times, 0.98 times 25 all over 1,000 gives me 0.0245 moles. Okay, so look at the moles I've got there and the moles I've got here. So this number is bigger than this one, which makes sense because they've just added that. Yeah. So what that means is get the bigger take the bigger one, 0.0245, minus the amount used in the hydrolysis process. I'm going to get an excess number, minus 6.06 exponential minus 3. That gives me 0.01844 moles of sodium hydroxide left over. Now they're saying to assume it's in 25, so I need to turn that back into concentration. So reorganize this for concentration. So times that by 1,000, bring 1,000 up, times it by 1,000 divided by V, divided by 25. Times 1,000, divide by 25, and I get a new concentration of 0.738 moles per dm cubed. Now that I've got the concentration of the sodium hydroxide, I can work out its pH. So Kw equals H plus multiplied by OH minus, and I know Kw, it's given it to me, so Kw over the OH minus concentration will give me H plus 1 exponential minus 14 divided by answer, which gives me 1.355 times 10 to the minus 14 minus log answer. Yeah, I'm going to do that and then minus log answer, and I now get a pH of 13.87. pH. Does it say to give to one decimal place? No, it doesn't, so that's fine. Two indicators, methyl orange and phenolphthalein, were available for this titration. Student A thought methyl orange could be used, phenolphthalein could be used, suggests either, and the answer is C. Student C is correct. Student C is correct. Now, the reason why, guys, is the titration we were doing, with sodium hydroxide and HCl. That's what they told us. Sodium hydroxide and hydrochloric acid. That's a strong acid, strong base. The strong acid, strong base. Yeah, the vertical region's massive. Phenolphthalein changes up here. Yeah, and then methyl orange changes here. Both of their changes are within the vertical region. So both indicators will change color in the vertical region, of the graph. Done. Moving on. Describe how sodium ethanoate in the final reaction mixture could be converted into ethanoic acid. Right, so they're saying that we've got sodium ethanoate because it was in alkali solution. If I want to convert that back into ethanoic acid, I need to add excess hydrochloric acid to push the H plus back on. Add excess HCl solution. We're done. Next. Buffers. Oh my God, how are we doing for time? 1 hour 38. How far are we from the end? Is this the last one? No. That is, though. So close. Okay, ethanoic acid can be used to form buffer solutions. Calculate the pH of a buffer solution where 50 centimeters cubed of is added to sodium hydroxide. Oh, it's a tricky one. Right, guys, first things first. This is a buffer. We're going to write our buffer roadmap. H plus, and we're going from a ethanoic acid buffer. So that's the ethane ethanoate ion, and CH3COOH. This is our buffer roadmap. So in order for us to find the pH, this is what we're looking for. We have currently got Ka, which is great, 1.7 times 10 to the minus 5. What we now need to do is find out the concentration of him and the concentration of him. Now they have added ethanoic acid with sodium hydroxide, which means for it to be a buffer, there must be excess weak acid. So first thing we need to do is and it's given us concentrations of everybody. So we need to do original acid. So the original acid is number of moles equals C times V over 1,000. There's my equation, so important. The V there and the concentration is there. So 0.15 multiplied by a volume of 50 all over 1,000. This is going to give me the moles of original acid. 0.15 times by 50 all over 1,000, which gives me 7.5 times 10 to the minus 3 moles. Next, now I need to do moles of sodium hydroxide, moles of NaOH, and that's given me 0.142 times by 30 all over 1,000, which is lower than the other guy. 0.142 times by 30 all over 1,000, which gives me 4.26 times 10 to the minus 3 moles. Now, the sodium hydroxide is going to neutralize the acid and become the salt. So that there is going to become, the COO minus. Yeah. So now we need to do excess acid. So the excess acid is 7.5 times 10 to the minus 3 minus 4.26 times 10 to the minus 3. It is also a 1-to-1 ratio, by the way, guys. So this makes it a little bit easier. Yeah, exponential minus 3 minus answer. I get 3.24 times 10 to the minus 3 excess acid moles. Now what we need to do is to convert both of those into concentration because my volume has changed. I added 50 to 30, which means it's now in a total of 80. So now I need to say the concentration of the excess acid, is equal to the moles times 1,000. Yeah, times 1,000. I've just reorganized my equation over the new total volume of 80, because that was 50 centimeters cubed of whatever it was and 30 of the other guy. So the answer on my calculator is still there for the acid, so I may as well stick with that, times 1,000 divided by 80. So the concentration of the acid is 0.0405 moles per dm cubed of the acid. Now we need to find out the concentration of the salt. Yeah, now the concentration of the salt is the moles of the sodium hydroxide will become the moles of the salt. So I now have the moles of the sodium hydroxide was 4.26 times 10 to the minus 3 times 1,000 over 80, because the sodium hydroxide becomes the salt. So 4.26 exponential minus 3 times 1,000, the exponential minus 3 just disappears, divided by 80, and I get a value of 0.05325. Now I can insert those directly into my Ka equation, reorganize it. So Ka equals H plus. Now, this was A minus all over HA. So this is the acid, bring the acid over, times by the concentration of the acid. By the way, in the exam, I'd be very careful not to go over those lines. Yeah, so I'm going to do square brackets. So this is the concentration of the acid, which is 0.0405, divided by the salt, 0.05325. 5325, the moles of the salt, concentration of the salt. That will give us H plus. So 0.0405 multiplied by the Ka, 1.7 exponential minus 5 from the top. Yeah, divide that by 0.05325 equals, and I get a H plus concentration of 1.29 times 10 to the minus 5. Now, I always say that acidic buffers should be around the 4.5 mark. So let's now minus log answer, and I get pH 4.88. Very reasonable. Right. Oh, God. A small amount of sodium hydroxide and hydrochloric acid are added to separate samples of the buffer. Explain why these samples will resist pH. Illustrate your answer with at least 2 equations. Okay. So a buffer solution. So definition of a buffer. Yeah, definition of a buffer. A solution which resists change in pH on addition of small amounts of acid or base. That's the definition of a buffer. Now I need to explain why. The reason being is in a buffer you have a reservoir of acid. So this is our acid reservoir. Yeah, and it is in equilibrium with our conjugate base reservoir, our CBAS reservoir. And what we realize happens here is that when you add H plus to the mixture, when you add acid, the equilibrium will shift to remove it. So there's equation number 1. On addition, on adding acid, the H plus ions react with the CH3COO minus ions, removing them. Equilibrium shifts to the left, shifts to the left. Ratio, not ration, ratio of acid to base remains almost constant. Gotta say the word almost. Okay, now the next thing is the base one. So now what happens when we react it with sodium hydroxide? So if we react it with sodium hydroxide, the OH minus ions will react with the acid, and they will push the equilibrium that way. Second equation. So on adding sodium hydroxide, the OH minus ions react with acid, removing them. Equilibrium shift left. No, shift right. Shifts right. Ratio of acid and base remains almost constant. And I think almost constant. I think I'm done. Holy moly. 5 marks. Don't know if I've hit it. We'll find out, I guess. Guys, that's it. Right, the paper. Oh my God, that was a long paper, folks. Really long. My laptop's sticky. Right, that was a 1 hour 45-minute paper, and I'm done in 1 hour and 48. That's all. Thank you so much for giving up your time, Mr. Duncan. Oh, Nikita, you're more than welcome. Got to mark it now. But I was just in time for that. And I've done quite a lot of explanations, I feel. Maybe it's not as many as I would have liked. But let's have a look at the marking. Still sharing the screen, I think. I hope so. Yeah, still sharing the screen. Right. Can I please emphasize to all my students, if you do a paper, you must mark it straight away. If you don't mark it straight away, there's no point in doing this. And look, I've just spent an hour and 48 minutes doing this paper with you live on the internet. And I'm not going, oh my God, I need a break. No, it's not how this works. If you don't mark it straight away, you will get nothing out of this paper. Yeah, you cannot walk away yet. Right. The only thing I'm going to do is I'm just going to mark it and look for any mistakes. So I'm going to mark, here we go. Number 1, A. I'm happy with that. The acyl chloride has the lowest pH. B is A to form the unsubstituted amide. C is going to form a precipitate. Question 2 is C. It's the optically active one. That took my time on that one. Condensation reaction, B. Number 4. I'm going to form the sodium salt. Have I made a mistake? No, thank goodness not. I thought I'd suddenly not looked at the numbers carefully enough. We're good. It's A. Next one, the only diagram is C, because, yeah, those are the incorrect arrows. PCl5 converts an OIC to an acyl chloride. B had the highest entropy change. D had the equilibrium shift at 4.8. Next one, A, the sum of the hydration enthalpies. I actually thought the multiple choice on this paper was actually really nice. Same amount, D, 11, B, 12, C. Doing well on the multiple choice so far. This was horrible, didn't like this question one bit, 13. C, 1 and 4, this approach from the right, stupid. Equilibrium will react slowly, that good, I'm glad about that, yes. So I can titrate directly because the equilibrium will react slowly to it. Graph C is correct. Carbon monoxide, 15A is D. And then stupid one where they tried to trap me. 1.3 times 10 to the minus 2, winner. I'm doing really well on the multiple choice. Z, W, X, Y, 2. Okay, this is starting to get wordy now. 4.2 quartet due to 3 hydrogen atoms on the adjacent carbon. They've not mentioned a non-equivalent, but that's fine. Peak triplet, yeah, fine. Is the right structure for me. Thank you very much. 2 branches. Right, origin start line above the bottom of the paper. Start line, straight line for solvent from added, front added and labeled. Nice. Ignore omission of original spot. Spot due to position consisting of an RF value. I like it. I'll take it. Remember, focus on labeling. I should have done that baseline with a straight line, and I should call it the start line rather than baseline. So mental note, start line. Yeah, making those adjustments for me as well. Okay, I didn't like this question at all. Mark 1, 2-mark question. As only London forces form when ethyl ethanoate is polar, hexane is non-polar. Only London dispersion forces. Weaker interactions between the hexane is less soluble than hexane. A lower affinity for the mobile phase. Yeah. Did I mention solubility? Okay. Have they done allow solvent, mobile phase, reverse argument? It wanted you to talk about solubility, not affinity. Mental note. For TLC, solubility comment needed. I'm still going to talk about the affinity for, but I'm going to add in a solubility comment to my next TLC question. Oh my God, this was disgusting, this question. Did not like this at all. Okay, both react with 2,4-DMP to form a yellow, orange, red precipitate. That was my last point. Both can be reduced by lithium tetrahydroaluminate. Should have made that more specific, bit unclear there. Propanal, but propanal forms primary alcohol, propanone forms secondary alcohol, except named alcohols. Fine. Equation for the oxidation process. Propanol will react with acidified potassium dichromate. Propanone won't. Observations named orange to green. Take it. Hard that. Did not like that question one bit. This graph was full on disgusting. 1.9 times 10 to the minus 3, minus 6.4. The most disgusting graph ever. Axis correct way round and labeled. Numbers used on x-axis are without powers. Do not award F1 if given with LNK on y-axis. LNK on y. Have I got them the wrong way around? Do not award if units given for LNK on y-axis. Oh yeah, there's no units for LNK. Have I got this the right way around? Ignore y-axis with increasing negative values going upwards. Okay. It is the correct way around though, right? Suitable, of course it is. Suitable scale for points, all points plotted correctly. I'll give myself 3. It takes time to do those, guys. Okay, gradient. So my gradient needs to be minus between these numbers. Look, you can see the numbers there, guys. Between those numbers, mine is spot on within it. The units are in Kelvin and calculation of the activation energy. Therefore, the activation energy will be anywhere between those values, which mine is. Oh, the stupid comments. I hate it when they say comment on anything. The value is large in comparison to others, so the value is large. As lots of energy or the reaction is kinetically stable, rate of reaction is low. High temperatures will be needed, lots of energies will be required, fine. So the reaction requires very high temperatures, perfect. Next, didn't like this one either. As T increases, K increases rapidly, brackets not needed, but fine. As the average energy of molecules increases, particles gain more kinetic energy. So many more particles have EA. Okay, on to our crazy entropy. Expression, values, yeah, 7.8, perfect. Expressions, always worth a mark as well, guys. Look, expression, 2 marks for the equations. Well, I've guaranteed those if I just throw them down. Yeah, then it says work out the surroundings. Yeah, then it says work out the total. Like it. At 700, we get used to these questions. We know that these are super common. Higher temperatures would result in a less positive surroundings. Delta S surroundings will be smaller. Delta S total, therefore, will also be smaller. I'm going to add in a point here, guys. I'm saying smaller. Do they allow it? I shouldn't say smaller. Don't do that. Less positive. Please, please, Mr. Duncan, make that change. Make that change. Less positive. I'm going to deduct myself. I'm going to give it to myself, but I probably would have in the real thing, but I don't like it. I need to say less positive. That's important for me to make that change. Therefore, lower yield makes the reaction less feasible. Lower yield. Higher temperatures will increase rate. Fine. Calculate a value for the rate constant K. Oh, what's the range? Oh, I am just in it. Holy mackerel. Like to the wire there, folks. Wowzer. To the wire. Fine. Oh, God. Born Harbors. D times 2, so arrows, B, C, E times 2, F. Arrows going up, 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 down, and down. Tick, tick, tick. F, all good. I hope everyone agrees. Look, yeah, it's nice to see that mine matches theirs perfectly. Yeah, I like it. I probably should have put the times 2 on the outside, like they did. Something to bear that in mind, I think, definitely. Then it's going to say work out all my values. Work out my value. Oh, this one's always a bit rough. This one, perfect. Still got the numbers. Easy to make a calculator error. Next, bonding in calcium fluoride is almost 100% ionic, whereas bonding is a degree of covalency. Calcium ion is polarizing. Fluoride ion so small, not easily so large. Right, I missed one. Oh no, 4 marks. That's fine. Reverse argument. It's fine. Thought I'd lost one. Thought it was a 5 marker. Fine. The electron affinity is more exothermic. As the chlorine is smaller, stronger attraction. I like it. Horrible name. 3-methyl butyl, 1-butyl ethanoate. Do I need the 1? Oh, yeah, the original one. Yeah, fine. I looked at the ore. 73%? Yeah, 0.6%. Winner. I was really concerned about this one. pH 3.87. Yeah, winner. I was really concerned. It seemed very high to me. Student C is correct. Both methyl orange have a color change in the equivalent vertical section of the graph. Add excess HCl. pH 4.88. This is always a big one. Oh, I've got 8.9. I've got 8.9. Oh, I'm out. I'm not. I'm out by 0.1. That sucks if I got a rounding error. So close. I'm going to give myself 4 and say watch out for rounding errors, Mr. Duncan. I'm pretty sure everything else tallies. So there's that one. That's the first one up at the top. Yeah, and then the next one, the original. Yeah, the original, which is there, gives us the change 1. Yeah. And then new concentration over 80. Yeah, all over 80s. So I'm going to give myself 4 because I feel like there's a rounding error somewhere, but it's something for me to bear in mind. I'm pretty much there, though. Okay, final question. Large reservoir. I like it. OH minus reacts with the acid to form the salt. Oh, I didn't balance it. I'll lose 1. Definitely lose my equations. I need water. I should have. The other one doesn't, actually. Yeah, the other one doesn't, but that one does. Definitely lose 1 mark on that one there, guys. Yeah, but same, the ratio of acid base remains almost constant. H plus reacts, all that jazz. So I'll definitely give myself 4, but I'll lose 1 for an imbalance equation. Right, guys, what an entertaining 2 hours that has been. Wowza. That's been intense, man. Oh, Nikita, did you manage to make it to the end? Anyway, guys, I hope... Stop screen. I've just done stop screen. Guys, I hope you have found it useful. Keep working hard, everybody, and I'll see you guys next time for paper 5. See you later, everybody.